Well, the way I do that is I look for a common multiple of 7 and 2. What is that? 14. So I'm going to turn them into negative 14, positive 14. All right, now y'all pay attention because this is where students get confused. If I want this number to become negative 14, what do I have to multiply that number by?
Positive 2.
2. Positive 2. See you later. But if I multiply one part of an equation by positive 2, then I have to multiply every part of that equation by positive 2. That means this side also. A very common mistake that students make is they forget about the constant term on the other side. Every part needs to be multiplied by 2. Now, if I want this 2 to become a positive 14, what do I multiply by? 7. But that means I need to multiply everything by 7. So in this case, James, we multiply both equations, not by the same number because that won't achieve our goal. All right? All right, so let's see what we've transformed these equations into. The first one is now 6x minus 14y equals negative 28. The second equation is now 35x plus 14y is equal to 315. Now analyze your variables. Do you have one that's going to be eliminated? The y variable will be eliminated because positive 14 and negative 14 is 0. And so I add the two columns that are left. 6 and 35 is 41. X. Keep your equal sign where it is. Negative 28 and 315 is 287. Simple equation, one letter left. All I have to do is divide by 41.
7.
And it is 7. Okay? But I'm not done because I need to know what y is. Now, I recommend you plug this into one of the original equations before you did any transformations.
So you can take that number and plug it into 3x minus.
Yes. Because this first equation is the same thing as this equation. It's just to a higher multiple. Okay? You could plug it into this first equation, this equation, this equation, or this equation and get the right answer. Because all of those have the same x and y. I say choose the one with the smallest numbers. I would choose this one. Well, no, this one. Because it has the smallest numbers. All right, so if x is 7, then 3 times 7, let's come back down. What's the rest of the problem? Minus 7y equals negative 14. So 21 minus 7y equals negative 14. Subtract 21 from both sides. Negative 7y is equal to negative 35. Divide by negative 7. What's y? 5. So the point where those two lines intersect is where x is 7 and y is 5. And we must put it as an ordered pair because it does represent an actual point on a graph. Elimination and substitution. That's it. Does elimination do you have to use one or the other at specific times? No. Either one will work. But sometimes one is easier than the other. For instance, if you see that through substitution you're going to have to work with fractions, then it may be better to use elimination. Because then you won't have to work with fractions. If you see that trying to work with elimination is going to cause a problem, you may want to use substitution.
Can you do a substitution?
Okay?
Can you do one where one of the variables is not by, like if both variables have like 2y or 2x, it's the ones on the quiz that would mess me up. Like usually it's 2x minus y equals what, and then you just leave negative. Like it's real easy because y is by itself, but if there's the variables of both multiply.
I know what you're saying. Okay, let's look at one. Okay. In this case, it seems like the easiest thing to do would be to divide everything by 7, right? But that's really not the easiest thing to do because then you're going to have to work with fractions. And when we start working with fractions, there's more room for error. So here, since all these numbers are even, I'm not going to have to work with fractions. Because if I move the 4y to the other side by subtracting it, and now I want x by itself, so I divide by 2, but then I have to divide everything by 2. I have found the phrase that x is equal to, and I don't have fractions. Okay? So x is equal to 3 minus 2y. So I'm going to substitute that into the other equation for x. So 7 times 3 minus 2y is equal to 4 plus 3y. X is eliminated, it's gone. Let's solve for y. Start with distribution. This is 21 minus 14y is equal to 4 plus 3y. What would you do? Would you bring the 14y to the right or the 3y to the left?
3y.
And does it really matter which one you do? No, but it's easier if we try to keep our y's positive, okay? Because that's just less room for error. If I add 14y to both sides, then that means I need to bring 4 over here, right? So I'm going to subtract 4 from both sides. This gives me 17 is equal to 17. Y. What is the value of y? Finish it off. If y is 1, then x is equal to 3 minus 2. Because 2 times 1 is 2. So x is 1. The ordered pair is 1, 1. Now let's take that same system and solve it through elimination. And you're going to see that we still get 1, 1. Okay? All right, so the same system. Okay, let me find it.
You have it in standard form.
I have to put the second equation in standard form. Because all my stuff has to line up. All right, so the first one was 2x plus 4y equals 6. The second equation is 7x equals. Well, what needs to happen? I need to bring my y to this side. It says 7x equals 4 plus 3y. So when I bring 3y over to the left, it becomes minus 3y equals 4. All right, now if we were going to do elimination, my brain says, since I need one to be plus and one to be minus, and the y variables are already positive, negative, I'm going to take 4 and 3 and turn them into 12. Okay? Well, if I want this 4 to become 12, I have to multiply it by 3. That means I have to multiply everything by 3. If I want this to become 12,